Okay, we'll begin. And so we are in chapter 9, and it's week 9, and I hope everything is good. Okay, so here we are doing inference for numeric variables. And so as far as inference for numeric variables go, there are kind of 4 topics that we will cover, all right? And so we have confidence intervals, for mu based on one sample. We will also have hypothesis tests, for mu based on one sample. Okay. We will also have confidence intervals, for the quantity mu1 minus mu2 based on 2 samples. And hypothesis tests for mu1 and mu2 based on 2 samples. Okay, and so we introduced confidence intervals for mu based on one sample on Monday a little bit, and today we'll cover hypothesis tests for mu based on one sample, and then on Friday I'll cover these last 2 topics. It is a lot of information and a lot of stuff, but at the same time there's just there's a lot of overlap and parallels between confidence intervals and hypothesis tests for proportions and categorical variables as there is with numeric variables. And so I feel like if you're comfortable with the stuff for p, then we'll be comfortable with the stuff for mu. Okay, so let's just briefly create our confidence interval for mu based on a sample. Okay, so what we have in our middle, in the center, we'll put our best guess. Best guess for mu. And what's that? X bar, right? And then we go plus or minus a critical value times our standard error. So we'll go plus or minus. Our critical value is going to be t star, and our standard error is going to be s over the square root of n. Okay, we use s because we don't know what sigma is. We don't know the population standard deviation. T, the t star depends on our confidence level and the degrees of freedom which is equal to n minus 1. So our degrees of freedom df is equal to n, our sample size, minus 1. Okay, and that's because if someone tells you the sample mean of something, like we could play a game, and I could say, I can promise that I can make sure that the average of these 10 numbers is 50 or something like that. Okay, I could say, yes, you can pick any 9 numbers you want. As long as I get to pick the 10th number, I can make sure that the average of these 10 numbers is 50, right? And all I have to do is just make sure that when I add up all 10 numbers, it adds up to 500. And so, in essence, you have 9 degrees of freedom because I get to pick the last one to make sure that the sample mean is what I want it to be. And so we have degrees of freedom is n minus 1. Okay, and so let's say we had a sample size of 21, then I would have 20 degrees of freedom. And if I want a 95% confidence interval, then at 20 degrees of freedom and 95% confidence, the critical value I would use is 2.086. Let's take a look here. So at 20, if I have n equal to 21, at 20 degrees of freedom, I'm in this row. And then I look at the column at the top where it says confidence level, and I would see 95% at 95% in that column, and 20 degrees of freedom, the value I use is 2.086. Do we see that? I hope. Okay. 2.086. So okay, so let's try an example here. Okay. So let's say let's make a 95% confidence interval for the population mean weight of we'll stick with our dairy cows, Jersey dairy cows. Okay, and then so we will say you take a random sample of 15 cows. Okay, and then so you get your measurements are something like one cow was 1,483 pounds, and another cow was 1,576 pounds, and another one was 1,644, or whatever, etc., etc., etc. Okay, so you have a total of 15 measurements. Okay, and then we would say we calculate our sample statistics. So the sample mean is 1,560 pounds. The standard deviation is 158 pounds. Okay, so I'll say the question here is, what is the lower bound of a 95% confidence interval? Okay, and you'll have some answer choices. This is a clicker question. Okay, your answer choices are these. Okay, so go ahead and try that out. So you'll have to use your table that you passed out. If you got here late and you don't have a reference table, come on down and get one. You'll need one of these. Okay, how are we doing? Just a few more seconds here to get your clicks in. Okay, so everybody click your remotes if you haven't done so. Clickety, click, click, click. Okay, I'm gonna hit stop here. All right, so let's take a look. Okay, so I'm just going to go through and label things. We have a random sample of 15 cows, so 15 is our sample size n. Our sample mean is 1,560. This is going to be my x bar. The standard deviation is 158. That's my s. Okay, and so my degrees of freedom will be n minus 1, so I will have 14 degrees of freedom, and at 95% confidence, my t star is going to be 2.145. Is that right? Okay. All right, so what I have is 1560 plus or minus 2.145 times 158 divided by the square root of 15. Okay, so I type in 2.145 times 158 divided by the square root of 15, and I get 87.51 pretty much. 1560 plus or minus, here I'm just rounding off to 2 decimal places, but so I got 1560 plus or minus 87.51, so my lower bound will be 1560 minus 87.51, and that gives me 1472.49. Okay. On the other hand, my upper bound will be 1560 plus 87.51, so I can do 1560 plus this number, and I get 1647.51. Okay, and so let's see how you guys did. Most of you guys got it. Okay, those of you who got it wrong, who selected A, you forgot to divide by the square root of n. And then if you selected this one, you picked the, you used the 15 degrees of freedom instead of n minus 1, 14 degrees of freedom. Okay, is that good with everybody? Okay, so 1472.49 to 1647.51. So we would say our 95% confidence interval goes from 1472.49 to 1657.51, and we would say I am 95% confident that the average weight or mean weight of all cows, of all dairy cows in the population, cows are all female, right? Because if it's a boy, it's a bull, right? Like it has to be, right? I think. Okay. All right. I'm 95% confident that the average weight of all dairy cows in the population is between 1472.49 and 1657.51 pounds. Okay. That's how you know you go to UCLA, is that we don't really know anything about farming. Being in urban, it'd be different if this was more rural. What? Yeah. So. Okay. All right. So let's ask just a few questions. So based on our interval, we'll say based on the CI, do we have evidence that the mean weight, the population mean mu, is 1,500 pounds? Yes or no? Okay, go ahead and click in your answers. Do we have evidence that the population mean mu is 1,500 pounds? Okay, who's clicking D and E? Your only answer choices are A and B. Okay, just a few more seconds, get your clicks in. I have two people, one that has clicked a C and one that's clicked a D, so just, okay, there he goes. Make sure you've clicked A or B. Don't click the other buttons. Okay, I'm gonna hit stop here. So let's see, all right. I'm gonna go ahead and ask the next question. And we'll say, do we have evidence that the population mean mu is not 1,500 pounds? Okay, again, yes or no. So do we have evidence that the population mean mu is not 1,500 pounds? Okay, again, just get your clicks in. I'll hit stop pretty soon here. So click, clickety, click, click. Okay, I'm gonna hit stop. Okay, let's go over our answers here. Okay, so do we have evidence that the population mean mu is 1,500 pounds? Okay, so we can say that 1500 is inside the interval because it's between 1472 and 1657. So this 1500 is inside the interval. Okay, but just like when we talked about confidence intervals for P, the interval never provides evidence that the mean is exactly some value. Okay, the interval does not say that the mean is exactly a particular value. Okay? So we would say no here. Okay? Do we have evidence that the population mean mu is not 1,500 pounds? Okay? So again, 1,500 is inside the interval. Okay, and we would say, so 1,500 is a plausible value. Plausible value for mu. Okay, and so therefore, we do not have evidence that mu is not 1,500 pounds. Okay, and so the answer here is also no. Okay, so let's see how you guys did. So you guys got it. Oh, okay, so this is what we have. Okay, and so again, the types of questions and conclusions we can make based on confidence intervals for P are the same kinds of conclusions and things we can make for confidence intervals with mu. Okay. On the other hand, if I asked about something being do we have evidence that the population mean mu is not 1,700 pounds? We would say yes, we have evidence that it's not 1,700 because 1,700 is outside of the interval. Okay. But 1,500 is inside the interval, so it is a plausible value. So we don't have evidence that it's not 1,500. Okay. However, we cannot say that it is 1,500. All right. I know we generally try to avoid double negatives, but we have to say it this way because not having evidence that it's not 1,500 is not evidence that it is 1,500. Okay. I know that we don't like it that way, but that's how it is. Okay. Okay, so that's confidence intervals. Again, if you review kind of the conceptual stuff for confidence intervals, whether it's for proportions or means, it works. Okay, it's just kind of the formulas have changed, but the reasoning has not. Okay, let's talk about hypothesis testing for mu with one sample. Okay, and so we can kind of break down our hypothesis testing into 4 steps. So step 1 is make your hypotheses. Okay, where the null hypothesis always has an equal sign, and this time because it's about the population mean mu, our null hypothesis will say mu is equal to some value, and the placeholder for that is mu 0, but just keep in mind mu 0 is a constant, and it's just some number. It's just a number. Okay, and then the alternative is identical to the null hypothesis, except the equal sign is replaced with something else. So we have mu not equal to mu 0, or mu is greater than mu 0, or mu is less than mu 0. Okay, so again, mu 0 is just some constant. So for example, you could have mu equal to 30 versus the alternative that mu is greater than 30, or something like that. Okay, of course, replace 30 with whatever number is appropriate for the question being asked. Okay, step 2 is our preparation step. So here we would check our conditions. I believe I already covered the conditions for using the central limit theorem with a numeric variable. Pretty much exactly the same as checking the conditions for categorical variables, except now we don't use NP. We ask, is n greater than 25, or is the population almost normal? Okay, and then identify or choose alpha. And what's the default level of alpha if one is not specified? Yeah, 5%. Okay, so default is alpha equal to 0.05 if one is not given. Okay, step 3 will be your calculations. Oh, something happened. Okay. So 3a will be find your standard error. So we have the standard error is equal to s over the square root of n. Once you have your standard error, figure out your test statistic, which is always our comparison between the reality or the observed and the expected. Observed minus expected divided by our standard error. So in this case, this would be our test statistic will take on the letter t, and it will be our observed is x bar. If the null hypothesis were true, we would expect to get mu 0, and we divide this by our standard error. And then finally, once you have your test statistic, you would look it up. Look up t in the table. To get a p-value. And so this part has changed. The use of the t-table is pretty different from using the z-table. So I'll devote the next couple slides to using the t-table. Okay, and then so once you get your p-value, the last step is to make your conclusion. And how do our conclusions work? Okay, if your p-value is greater than alpha, what does that mean? What do we decide? We do not reject the null hypothesis. Okay, and if the p-value is less than alpha, that means we do reject. The null hypothesis. Okay. So far so good? Okay. So as far as the steps in all of the stuff here, it's very similar to hypothesis testing when you have a proportion. Okay, it's just the way we calculate the standard error is a little different, and then our test statistic is now a t. Okay, I would say the biggest change is in using the t-table rather than the z-table. Okay, and I guess this is worth noting. For proportions, it's always the z table. Proportions always z. And for means, always t. Okay, so don't mix those up. Okay, if you're dealing with proportions, you're always going to use the z table. If you're dealing with means, you're always going to use the t table. Okay, let's talk about using the t table. So I'm just going to say you've done all of your other work. Okay, you got the standard error, you got your test statistic, and now we want to go from the test statistic to the p-value here. Okay, so let me copy this portion, part of the t-table. Okay, so let's say so you get t equal to, let's say, 2.43. Okay, t is equal to 2.43, and what you'll need is your degrees of freedom. So let's say we have 12 degrees of freedom. Okay, and then you also need to know what the alternative says. Okay, so we'll say the alternative has a greater than sign. So we'll say HA is mu is greater than 30 or something like that. Okay, so what do? We'd say, okay, well, at degrees of freedom equal to 12, okay, we're only going to just concern ourselves with this row right here. Okay, and we would say, okay, 2.43, if I look here, 2.43 fits in between 2.179 and 2.681. Okay, so in the row for 12 degrees of freedom, which means I had a sample size of 13, I have 2.43, and that fits in between 2.179 and 2.681. Okay, I then go to my column headings, and I see right tail probability, and it says t is 0.025 and 0.010. Okay, so what this means is that the corresponding tail area, the tail area is between 0.025 and 0.010. Okay, so because 2.43 is in between these two columns, my corresponding tail will be in between these two column headings of 0.025 and 0.01. Okay, and so we don't have an exact value for the tail area. So not an exact value, but we have a range. Okay, so okay, the only time, and this is very rare, but it could happen, the only time you would get an exact value for the tail is if your test statistic ended up being one of these numbers exactly. So if we had 12 degrees of freedom and you had your test statistic ended up being exactly 1.782, then your tail would be exactly 0.050. Okay? Otherwise, it's going to be in between some column headings. Okay? All right, and so I'll talk about the rules here. But in this case, our p-value is equal to our tail area when the alternative has a greater than sign. So here we would say our p-value is between 0.025 and 0.010. Okay, so or just 0.01 really. So even though we don't have an exact value, if our alpha were 5%, we know our p-value is less than alpha. Okay? Even if our alpha was 2.5%, 0.025, even if our alpha was 0.025, we know that our p-value is less than 0.025 because we know that it's between 0.025 and 0.01. Is that okay with everybody? Okay. So let me give you kind of the rules for going from a tail area to a p-value. Okay. So if the alternative has a greater than sign, then t, your test statistic, should be positive. Okay, you would look up the tail area, and your p-value is equal to the tail area. Okay, if the alternative has a less than sign, then t should be negative. Okay, ignore the negative sign because your t-table only has positive values, so ignore the minus sign. Okay, look up the tail area, and your p-value is equal to the tail area. If the alternative has a not equal sign, okay, then ignore the sign. Ignore the sign of t. Look up the tail area, and then your p-value will equal 2 times the tail area. All right. And then I'm going to just kind of put a little note, and I'll say, on rare occasion, okay, there is a mismatch between the alternative and sign of t. Okay, so again, so what here I said if the alternative has a greater than sign, then the t should be positive, and if the alternative has a less than sign, then the t should be negative. Okay, but sometimes there's a mismatch where you have an alternative with a greater than, and then your t ends up being negative. So that would count as a mismatch between the alternative and the sign of t. Okay, so in these rare cases, or in these cases, the p-value is equal to 1 minus the tail area. Okay, but again, I would say this is fairly rare, and so I would say you don't really have to worry about it. Okay. It would be something like, do we have evidence that I don't know, the average weight of cows is over 3,000 pounds or something like that, okay? And then when we gather data, the average weight of cows, if anything, would be less than 3,000 pounds, and so we would not have any evidence to say that the average weight is over 3,000. And so in that case, there would be a mismatch between the alternative and the sign of t. Okay, is that all right? So let's just try out another one of these examples here. Okay, and so let's say so this will be a problem for you. Okay, so let's say the alternative is mu is less than 25. You have degrees of freedom equal to 10, and we will say your test statistic ends up being negative 4.63. Okay, so the question is, what is your p-value? Okay, and so here are your answer choices. You have the p-value. Okay, let me just write these out. Okay, so go ahead and try this out. I don't know why this P came out all messed up. Okay, how are we doing? We got 113 responses, so just say a few more seconds, get your clicks in. There's like less than 2 weeks of school left, you guys. Just, yeah. Next week, you can hang out by the fountain. People will be having their little parties in there. The inverted fountain. Okay, all right, so I'm gonna hit stop here. All right, so we look, we've got 10 degrees of freedom, and then so we say, okay, we're over here, and we're going to ignore the negative sign, and we're gonna say 4.63 fits over here, okay? Which means our corresponding tail will go over here, okay? If we look at the column headings, we'll see that we have large tails over here and small tails over here. Whoops. So which means as we go this way, the corresponding tail will be less than 0.001. So our corresponding, well, I should say our tail is going to be less than 0.001. And here we have our p-value equal to our tail. So we got the p-value is less than 0.001. Likewise, if our test statistic ended up on this side, then the corresponding tail would be greater than 0.100. Okay. Okay, that's what we got for today. So we'll see you guys on Friday.